We have all absorbed the same instinct. To survive out there, in the cold and the dark, you seal yourself in. You build the strongest walls you can, close every door against the emptiness, and keep the world you need locked safely inside. It feels like common sense. It is also, it turns out, exactly backwards. A ship built to carry people to another star would be the most sealed object ever imagined. A world where every breath of air and every drop of water has to cycle inside a single hull for centuries. And the best sealed world we ever actually built, 8 people under glass in the Arizona desert, watched its oxygen slide from 20.9% toward 14.2% in only 16 months. On Earth, with rescue a phone call away. We cannot even agree whether such a voyage would need 98 people or 40,000. The enemy, it seems, was never the cold outside. It was the ceiling itself. Get comfortable. Hit subscribe if this is your first time here, because by the end of this, the word sealed will stop sounding like safety, and the open sky above you will look like the rarest thing in the universe. Now, let's slowly ease into this. Part 1. The Dream We Inherited. There is an image almost everyone carries, whether or not they have ever thought about it directly. It is the picture of a ship between the stars. Not a fighter, not a shuttle, but something slow and enormous. A sealed city turning quietly in the dark, its windows lit from within, sliding across the gap between one sun and another. Inside, generations are born and grow old and die, and somewhere far ahead, after centuries of patient travel, the great-great-grandchildren of the people who left finally arrive at a new world. You have seen it in films and on book covers and in the back of your own imagination, and it feels less like a prediction than like a memory of something that has not happened yet. We call this idea a generation ship. It goes by other names too: the multi-generational Starship, the World Ship, the Interstellar Arc, but the concept underneath all of them is the same. It is the idea that humanity could cross the impossible distances between the stars, not by going fast, but by going long. We would build a vessel large enough to carry not just people, but an entire way of life, and then we would simply wait, generation after generation, while the ship covered the distance at a speed our machines can actually reach. The travelers who set out would understand from the beginning that they would never see the destination. They would be the first link in a chain, and the chain itself would arrive. What makes this dream so seductive is that it seems to solve the one problem that wrecks every other plan for leaving the solar system. The stars are not just far away, they are far away in a way that breaks the human mind. The closest one to us is so distant that even light, the fastest thing there is, takes years to make the crossing. Every scheme that tries to get there quickly runs headlong into the laws of physics and shatters. But the generation ship does not try to be quick. It accepts the centuries. It says in effect that we do not need to outrun the distance if we are willing to outlive it. And in that single move, the problem appears to transform from something impossible into something merely difficult. I want you to notice how the challenge quietly changes shape when you accept that bargain. The moment you stop asking the ship to be fast, you stop caring quite so much about the engine. The engine becomes almost a side issue, a thing you can hand-wave, because whatever it is, it only has to push the ship up to some modest fraction of light speed once, and then mostly coast. The real burden moves somewhere else entirely. It moves onto the hull, onto the inside, onto the question of whether the little world you have sealed up can keep itself alive for as long as the journey takes. The question is no longer, how far can we travel? The question becomes, how long can a world last? That is the question I want to sit with tonight, because it turns out to be far stranger and far more unsettling than the smooth image of the gliding arc ever lets on. We are not going to ask whether we can build an engine to push a city to the stars. We are going to ask something quieter and much harder. If you sealed a piece of the living world inside a metal shell and cut it off from everything, no resupply, no rescue, no help of any kind, how long could it actually keep going before something inside it failed? How long could it last out there? You can already feel, I think, that this is a different kind of question than the ones we usually ask about space. It is not about rockets or speed or far-off planets. It is about closure, about sealing, about whether a thing cut off from the rest of reality can hold its shape. And the honest place to begin is to admit that the comforting picture we all carry, the lit windows in the dark, hides almost everything that actually matters. Think of it for now as a world in a bottle, a whole living world, corked up in glass and steel, set adrift. It is a beautiful image. Hold on to it, because by the end of tonight, that bottle is going to mean something very different than it does right now. The dream is older than the rockets that might one day carry it out. More than a century ago, the Russian schoolteacher, who first worked out the mathematics of spaceflight, imagined that humanity would one day travel beyond the solar system in great enclosed vessels, calling such a ship a kind of ark, a Noah's Ark for the species, carrying life across an ocean far wider than any flood. The image has recurred ever since, in the work of scientists and novelists alike, because it answers something the human imagination keeps reaching for, a way to believe that we are not trapped here, that the walls of the solar system are not the walls of our whole story. What gives the dream its particular warmth, I think, is the relay. In ordinary life, we are used to the idea that we will not personally finish most of the things that matter most, that we plant trees whose shade we will never sit in, that we raise children to carry on after we are gone. The generation ship takes that quiet, familiar form of hope and makes it the entire structure of a voyage. No one finishes it. Everyone hands it on. The grandparents who board know they are giving their lives to a journey that belongs to strangers not yet born, and there is something almost unbearably moving in that, a generosity stretched across centuries. It is precisely because the idea is so emotionally satisfying that we so rarely stop to ask whether it could actually survive contact with reality. It is worth separating this dream cleanly from the other way people imagine reaching the stars, because the two could not be more different in spirit. One vision is the sprint, a tiny probe or a frozen sleeper hurled outward at a fierce fraction of light speed, betting everything on going fast enough to arrive within a single span of time. The generation ship is the opposite temperament entirely. It is the marathon run by a relay team that will never meet, the patient bet, the choice to accept that the crossing will swallow many lifetimes and to build a way of living that can be sustained for all of them. It does not try to cheat time. It tries to befriend it, to make a home inside the waiting itself. That is what makes it feel so achievable on first glance, and it is also exactly what makes it so quietly impossible, because befriending 1,000 years means asking a sealed world to do something nothing sealed has ever done. Before we can ask how long the bottle could last, though, we have to understand exactly how long it would need to, and that number, the length of the voyage itself, is where the dream first begins to stretch and thin. Part 2. The first crack. Let us start with the distance, because everything else grows out of it. The nearest star to our Sun is a small, dim red dwarf called Proxima Centauri, and it sits about 4¼ light-years away. The more precise figure is roughly 4.24 light-years, which works out to something close to 40 trillion kilometers. That number is already past the point where intuition can follow it, so let me try to give it a body. If you shrank the entire solar system, all the way out to the orbit of Neptune, down to the size of a coin held in your hand, then the nearest star on that same scale would still be a few kilometers away. Almost all of space is the emptiness between the coins. Proxima is not just the closest star, it is also, as we now know, a star with at least one planet, roughly the mass of Earth, orbiting in the zone where liquid water could exist. That is precisely why it has become the favorite destination in every serious discussion of generation ships. It is the closest thing we have to a door, and yet even this closest of all doors is almost unimaginably far. Consider the fastest object human beings have ever flung outward. Voyager 1, launched in 1977, is now drifting through interstellar space at about 17 kilometers per second. That is roughly 38,000 miles per hour, a speed that would carry you from one side of a city to the other before you finish the thought. It is the swiftest thing we have ever built that is leaving the solar system for good. And if you pointed Voyager at Proxima Centauri and waited, it would take somewhere between 73 and 75,000 years to arrive. Let that settle, not 75 years. 75,000. That is longer than the entire history of our species as recognizable modern humans. If a band of our ancestors had launched such a ship at the height of the last ice age, it would only now be approaching the halfway mark. So, our fastest real machine is hopelessly, almost comically too slow, which means a generation ship would need to go far faster than anything we have ever made. Suppose we could somehow reach 1% of the speed of light. That is about 3,000 kilometers per second, a velocity so far beyond our current engineering that we have no honest idea how to achieve it for something as heavy as a crewed ship. Even at that blistering, fantastical pace, the crossing to Proxima would still take more than 400 years. And 1% of light speed may itself be wildly optimistic for a vessel massive enough to carry a self-sustaining world. Many serious studies assume something more like half of 1%, which stretches the journey past 850 years. You will sometimes hear about faster concepts, and it is worth being clear about why they do not rescue us here. Designs like Project Daedalus and its later reworking Project Icarus imagine fusion-powered probes reaching 10 or even 12% of light speed, which could cut the trip to the nearest stars down to mere decades. But those are not arcs. They are tiny, fragile, uncrewed darts, scientific instruments the size of a building flung past a star to take pictures as they scream by. A generation ship is a different category of object entirely. It has to carry farms and forests and water and people, and the shielding to protect them all, which makes it millions of times heavier, which makes it far, far slower. The faster the probe, the lighter it must be, and a world cannot be light. So we are left with a sobering planning horizon. For even the very nearest star, a realistic crewed generation ship is looking at a voyage of centuries, quite possibly more than 1,000 years. And here is where I want you to stop thinking about kilometers and start thinking about something else, something that the smooth dream never makes you reckon with. The thing that actually has to survive this journey is not measured in distance. It is measured in human lifetimes. A voyage of 1,000 years is not a long drive. It is 10, 20, perhaps 40 complete human generations, each one born inside the ship, raised inside the ship, growing old and dying inside the ship, handing the mission to children, who will hand it to children of their own, none of whom will ever stand on the world they are travelling toward. That changes what the ship even is. A vehicle is something you ride to a destination, but no one rides a generation ship to its destination. The people who board it are not passengers in any ordinary sense, because boarding it means accepting that you, your children, and your children's children will live their entire lives in transit and die in the dark. The ship is not a vehicle at all. It is a habitat. It is a small, sealed world that has to keep functioning continuously, without interruption, for longer than almost any human institution has ever lasted, longer than most countries, longer than most religions in their recognizable form, longer than the time that separates us from the building of the great cathedrals. A light year is one of those phrases that gets used so often it stops landing, so let me slow it down. A light year is the distance light travels in a year, moving at about 300,000 kilometers every second, never resting for 365 days. That is a distance of nearly 10 trillion kilometers in a single year. And the nearest star is more than 4 of those distances away. When you look up at Proxima's neighbors in the southern sky, you are seeing light that left them more than 4 years ago, light that began its journey toward your eye before some of the things in your own recent memory had happened. Try anchoring the timescale to human history instead of to kilometers, because that is where it truly bites. A voyage of 1,000 years is the span that separates us from a world of stone castles and no printing press, a world before almost every nation and institution you know existed in its present form. Now imagine a single sealed community that had to keep functioning continuously across all of that change. The same closed system running from the age of knights to the age of spaceflight, never pausing, never resupplied, never allowed to fail even once. That is the demand a generation ship makes, except that the community would be sealed inside a metal hull the entire time, with the unbroken dark pressing on every window, and no new land ever appearing on any horizon to break the sameness of the years. Number the generations, and the strangeness sharpens. If a single generation is roughly 25 to 30 years, then a 1,000-year voyage means something like 35 generations of human beings living and dying between the launch and the arrival. The first generation says goodbye to a real sky they will never see again. The middle generations, perhaps 15 or 20 of them, will never have seen the sky of origin and will never see the sky of destination either, living their entire existence in the windowless middle of the journey, born in transit and buried in transit, knowing the stars only as fixed points that never seem to move. They are the true inhabitants of the generation ship, not the romantic pioneers at the start, nor the lucky arrivals at the end, but the long line of people in between, for whom the ship is simply the only world there is, the whole of reality from first breath to last. And the moment you see it that way, the central problem of interstellar travel quietly turns inside out. We started by worrying about how to cross the distance. But the distance, it turns out, is the easy part to describe. You point the ship and you wait. The hard part, the part that will decide everything, is whether the little world you sealed inside can hold itself together for all those centuries while it waits. The challenge was never really out there, in the gulf between the stars. The challenge was always going to be inside the hull. And that is the thread we are going to pull on for the rest of tonight. Because once you start tugging at it, the whole comfortable picture begins to come apart in your hands. Part 3. The enemy was never the distance. Once you accept that the voyage will take centuries, a strange and quiet truth moves to the front of the problem, and it is this. Everything the people aboard will ever breathe, drink, eat, or be physically built from has to already be on the ship when it leaves, and then it has to be used again and again and again for the entire length of the journey. There is no port to stop at. There is no supply convoy following behind. The atoms that make up the air in the first child's first breath are the same atoms that, centuries later, will have passed through countless plants and lungs and soils and rivers and bodies to become the air in the last child's last breath. Nothing comes in. Nothing useful goes out. The ship is a sealed loop, and the loop has to run without stopping for 1,000 years. This is the idea I want to plant firmly tonight, because it is the real center of the whole question. A generation ship is the most ambitious closed system anyone has ever proposed. Every other closed system we have ever built or studied has been small or short-lived or both. This one would have to be a complete living world, and it would have to stay balanced for longer than recorded history. And the trouble with closed systems, the reason this is so much harder than it sounds, comes down to one of the most unbreakable rules in all of physics. It is the second law of thermodynamics, and in its plainest form, it says that left to themselves, things fall apart. Order does not maintain itself for free. Concentrated, useful energy spreads out and becomes useless. Differences even out. Structures decay into formlessness. The universe, as a whole, is always sliding from order toward disorder, and that slide has a direction, and it does not reverse on its own. Now, a living thing seems to defy this, and in a sense it does, locally and temporarily. A tree builds itself into an intricate structure, a body holds its shape, an ecosystem maintains a balance for thousands of years. But none of these things actually break the second law. They hold off disorder only by constantly importing fresh energy and exporting waste. A tree drinks sunlight and pours heat and spent material back into its surroundings. A body eats and breathes and excretes. The order inside is paid for by an even greater disorder dumped outside. Life is not a violation of the law of decay. Life is a very elegant way of staying ahead of it, and the staying ahead requires a constant, unbroken stream of energy flowing through the system from somewhere else. Here is where the sealed ship runs into trouble. You can give it energy. A reactor or a great collector can pour power into the loop, and that is essential, and it is assumed in every design. But energy alone is not enough, because the matter is finite and it has to cycle perfectly. Every atom of nitrogen has to come out of the soil, pass through a plant, into an animal or a person, back out as waste, get broken down by the right microbes, and return to the soil in a usable form, over and over, with no losses that accumulate. And the brutal fact is that real cycles are never perfect. There is always some leak, some drift, some slow drift of material into a form that the loop cannot recover. A trace element that keeps getting locked into a mineral nobody can dissolve. A gas that keeps getting absorbed somewhere it cannot be released. A microbe that quietly evolves to do something slightly different than the one before it. Each of these losses is tiny. But you are running the loop for 1,000 years, and tiny losses, repeated through tens of thousands of cycles, do not stay tiny. This is what I mean when I say the enemy was never the distance. We began this whole story afraid of the gulf between the stars, the light years of nothing, the cold and the dark outside. But the cold and the dark out there are passive. They do nothing. They just sit there while you coast through them. The thing that will actually try to kill the people on the ship is not outside the hull at all. It is inside it. It is the patient, relentless tendency of every closed loop to drift out of balance, the slow accumulation of small failures, the steady pressure of the second law leaning on every cycle the ship depends on. The danger is not the journey. The danger is the box. And this completely reframes the title question. When we ask how long a generation ship could last, we are not really asking about fuel or speed or even hull strength in the obvious sense. We are asking something much subtler. We are asking how long a sealed loop of air and water and soil and life can be kept in balance before one of its countless cycles drifts far enough to break. We are asking how long order can be maintained inside a box that is cut off from everything. And that is a question we cannot answer by pointing at a star chart. We can only answer it by looking at the times we have actually tried to seal a piece of the living world inside a container and keep it running. You can feel the second law working in the smallest moments of any ordinary day, even if you have never named it. A hot cup of coffee left on the table always cools to room temperature, and never once, in the history of the universe, has a lukewarm cup spontaneously gathered the warmth back out of the room to heat itself. A drop of ink, released into water, spreads until it is evenly grey, and never gathers itself back into a drop. Order disperses. Differences fade. Things mix and even out and run down, always in the same direction, and the arrow of that process never reverses on its own. That one-way slide is not a tendency or a habit of nature. It is one of the most reliable laws we have ever found, and it applies to the inside of a starship exactly as much as it applies to a cup of coffee. The crucial subtlety, the thing that makes closure so much harder than it first appears, is the difference between energy and matter. You can keep pouring energy into a sealed ship, and you must, because energy is what holds disorder at bay. But matter is different. The atoms aboard are all the atoms there will ever be, and they have to be used and reused without loss, which means every cycle has to return its materials in a usable form, perfectly, indefinitely. Energy can flow through an open door in the system. Matter has to run in a perfect circle, and perfect circles, in the messy world of real chemistry and real biology, do not exist. Every loop leaks a little, locks a little away, lets a little drift into a form that cannot be recovered, and across 10,000 turns of the cycle, those small imperfections are what the second law uses to bring the whole thing down. A physicist once put the matter of life and order with a clarity worth borrowing. Living things, he argued, survive by feeding on order itself, by drawing in highly structured energy and giving back the spent and disordered remains, paying for their own internal order with a larger disorder dumped into their surroundings. A generation ship would have to do this not for one organism, but for an entire living world, continuously, while sealed inside walls that allow energy through but trap nearly all the matter inside. It would have to keep drinking order and excreting disorder, and the disorder would have nowhere to truly go, only somewhere inside the system to be cleaned up and recycled again. Every act of cleaning costs energy and is itself imperfect, leaving a little more mess each time. That is the trap of closure, stated as plainly as I can state it. You can hold disorder at bay for a while, but inside a sealed world, the bill always comes due somewhere, and over 1,000 years there is a great deal of bill. The unsettling part, the part that should make you sit up even as you are drifting towards sleep, is that we have tried this. Not in space, but here on Earth, under the best possible conditions, with the sun overhead and engineers standing by. We have built closed worlds and sealed people inside them and watched what happened. And what happened was not reassuring. The smallest, best-funded, most carefully designed closed world we ever made began to fail within months, and it failed in a way that nobody had predicted for reasons that took years to fully understand. To see just how fragile a sealed world really is, we have to go to the desert of Arizona, to a structure of glass and white steel, and step inside. Part 4. The breath that nearly failed. In the high desert north of Tucson, there is a building unlike any other on the planet. It is a sprawling complex of glass pyramids and domes and a step tower, covering more than 3 acres, and from the outside, it looks like a greenhouse designed by someone who had been dreaming of other worlds. It was called Biosphere 2, the name chosen because the builders considered Earth itself to be Biosphere 1, the original, and the purpose of this strange glass world was tremendously ambitious. It was meant to be a complete, sealed, self-sustaining miniature Earth, a closed loop of life that could keep human beings alive with no input from outside except sunlight and electricity. It was, in every meaningful sense, a rehearsal for exactly the kind of sealed world a generation ship would need to be. On the 26th of September, 1991, 8 people walked inside, and the airlock was sealed behind them. They called themselves the Biospherians, 4 men and 4 women, and the plan was for them to live entirely off their enclosed world for 2 full years. Inside the glass were several miniature ecosystems, carefully constructed and stocked. There was a patch of tropical rainforest. There was a small ocean with a coral reef, complete with waves driven by machinery. There was a savanna, a marsh, a desert, and a working farm where the crew would grow all their own food. There were animals and insects and fish, thousands of species in all, chosen to form a functioning web of life. The whole thing had cost on the order of $200 million. It was the most serious attempt anyone had ever made to put a living world in a bottle and seal the cork. And, almost immediately, the bottle began to behave in ways no one had foreseen. The first and most dangerous problem was the air. Slowly, steadily, the oxygen inside Biosphere 2 began to disappear. It started at the normal level you are breathing right now, about 20.9% of the atmosphere. But month after month, that number crept downward. It fell to 19%, then to 17%, then lower. By early in 1993, after about 16 months, it had dropped to roughly 14.2%. To understand what that means for a human body, that is the oxygen level you would find high on a mountain at an altitude of around 4,000 meters, more than 13,000 feet. The crew, living at the bottom of their glass world, were effectively gasping at the top of a peak they had never climbed. They suffered constant fatigue. They were short of breath, climbing a single flight of stairs. They developed sleep apnea, waking through the night, unable to get enough air. Some of them could no longer finish a spoken sentence without pausing to breathe. I want to take you inside that experience for a moment, because the numbers alone do not carry the weight of it. Picture yourself as one of those 8 people, well into the second winter. You wake in the morning and you are already tired, the kind of tired that sleep does not fix. The light coming through the glass panes is the same bright Arizona sun, the same sky you have always known, but the air you are pulling into your lungs tastes wrong, thin and insufficient, like the air of a mountain pass you never agreed to climb. You start up a short flight of stairs, and halfway up, you have to stop and rest, your pulse pounding, your vision swimming slightly at the edges. Through the glass, only a few dozen meters away, you can see the desert floor, a service road, a parking lot. The ordinary world is right there. A telephone call would bring help in minutes. And yet, inside your sealed sky, the oxygen is quietly leaking away into the walls, a fraction of a percent at a time, and the brilliant scientists who built this place do not yet fully understand where it is going. 8 people, 2 years. On Earth, with the sun overhead and rescue a phone call away, and the most carefully constructed closed world in human history was slowly, silently running out of breath. The cause, when they finally pieced it together, was a lesson in how closed loops fail. The oxygen was not escaping through a leak in the glass, it was being consumed. The soil inside Biosphere 2 had been made extremely fertile, packed with organic matter to grow food, and that soil was alive with microbes. Those microbes were breathing, consuming oxygen, and releasing carbon dioxide far faster than anyone had modelled. In a normal world, the plants would have taken that carbon dioxide and turned it back into oxygen, closing the loop. But here, a second hidden process intervened. The structure was full of exposed, uncured concrete, and concrete absorbs carbon dioxide as it hardens, pulling it permanently out of the air. So the carbon dioxide that should have cycled back into oxygen through the plants was instead being locked into the building itself. The loop had a leak no one had designed and no one had seen, and through that invisible gap, the breathable air slowly drained away. In the end, to keep the crew safe, oxygen had to be pumped in from outside, which meant that the sealed world was no longer sealed. The closure, the entire point of the experiment, had been broken. The air was only the most dramatic failure. There were others, and each one taught the same lesson in a different key. Food was chronically short, especially in the first year, and the crew lost significant weight, several of them dropping to gaunt, hungry versions of themselves. The intricate web of life they had stocked began to unravel in unexpected directions. Most of the pollinating insects, the bees and others that flowering plants depend on to reproduce, went extinct inside the dome, which quietly threatened the long-term survival of every plant that needed them. Meanwhile, the species that thrived were not the ones anyone wanted. Ants spread through the structure, Cockroaches multiplied and overran whole sections. A morning glory vine that had been meant as a minor ornamental plant grew explosively and tried to smother the food crops. The carefully balanced ecosystem was not staying balanced at all. It was lurching, some parts collapsing while others ran wild, exactly the kind of drift that the second law promises in any system that is not perfectly maintained. And then there were the people themselves, living sealed inside a small world, hungry, short of breath, and under constant pressure. The 8 crew members did not pull together into a serene team. Within about 6 months, they had fractured into 2 hostile factions, divided over how the experiment should be run, and the rift grew so bitter that members of opposing groups reportedly could barely speak to one another by the end. The human part of the closed system, it turned out, was just as prone to drift and breakdown as the chemical and biological parts. The bottle had been sealed with 8 friends inside, and 2 years later it opened on 2 camps who could hardly stand the sight of each other. Part of what doomed the air in Biosphere 2 was something as ordinary as the weather, which is a lesson in itself about how closed systems get blindsided. The first year of the experiment happened to fall during a period of unusual cloud cover over southern Arizona, more overcast skies than the region normally sees. Less sunlight reaching the glass meant less photosynthesis from the plants inside, which meant less oxygen produced and less food grown, at precisely the time the hidden processes were draining oxygen away. The crew had built a world that depended on the sun, and the sun, for a season, simply gave a little less, and the sealed world had no reserve to absorb even that modest shortfall. A real starship would face the same brittleness, except that for it there would be no next season of better weather, only whatever margins it carried from the start. The most important thing Biosphere 2 proved was not that any single component failed, but that the failures came from couplings nobody had drawn on any diagram. No one had planned for the concrete to compete with the plants for carbon dioxide. No one had expected the soil microbes to breathe so hard. No one had anticipated that the pollinators would die while the cockroaches flourished, or that hunger and thin air would turn 8 colleagues into 2 factions. Each failure, traced backward, led to an interaction between parts of the system that the designers had treated as separate. That is the deepest warning the experiment offers. A closed world is not a collection of independent systems you can perfect one at a time. It is a single tangled web in which everything touches everything, and the failures hide in the connections, where they are hardest to see and hardest to fix. So this was the result of the most serious attempt humanity has ever made to build a sealed living world. It nearly suffocated its crew. It could not feed them properly. Its ecosystem spun out of balance, and its people turned on each other, all within 2 years, all while sitting in the Arizona desert with every advantage that being on Earth provides. Now hold that beside the thing we are actually imagining tonight. A generation ship would need a closed world like this one to function not for 2 years but for centuries. It would need the air to hold not for 16 months but for 16 generations. And it would have to do all of it, with no oxygen to pump in from outside, no engineers to cool, no parking lot a few meters beyond the glass. If 2 years on Earth nearly broke the bottle, the question of how long one could last in the dark between the stars suddenly looks very different. But Biosphere 2 was a first attempt, full of beginners' mistakes. Surely, you might think, we have done better since, somewhere, under more careful control. And in a cold facility in Siberia, decades earlier, a different team had in fact come closer than anyone before or since. Part 5. The Best We Have Ever Done. Long before Biosphere 2 rose in the Arizona desert, a quieter and in some ways more impressive experiment was running in the cold of central Siberia. In the city of Krasnoyarsk, at the Institute of Biophysics, Soviet scientists had been working since the 1960s on a problem they understood to be essential for any real future in space. They wanted to know whether human beings could be kept alive inside a closed loop of life, sealed off from the outside, breathing air and drinking water and eating food that the system itself regenerated. By 1972, they had completed a facility they called Biosphere, and it remains, even now, one of the most successful closed ecology experiments ever conducted. Biosphere was not large. It was an underground steel chamber of about 315 cubic meters, roughly the volume of a modest house, divided into compartments. There were small living quarters with cabins and a kitchen, a control area, and crucially, growing chambers filled with light and plants. The crews were small, just 1 to 3 people at a time. And the engine of the whole system, the thing that made the air breathable, was a combination of 2 kinds of photosynthetic life. There were tanks of microscopic green algae, a type called chlorella, which are extraordinarily efficient at turning carbon dioxide back into oxygen. And there were higher plants, including wheat, that the crew grew, harvested, and milled into flour to bake their own bread. The results Biosphere achieved were genuinely remarkable, and they still set the standard. The system recycled essentially all of the air the crew needed, with the algae and plants steadily converting their exhaled carbon dioxide back into breathable oxygen. It reclaimed about 95% of the water, purifying it and using it again and again. And it grew a large share of the crew's food, reaching something on the order of 80% self-sufficiency. For a sealed chamber under the Siberian ground, keeping people breathing and fed and watered largely from a closed loop of algae and wheat, this was an achievement that has rarely been matched. But notice the word largely, because it carries the whole lesson. Biosphere never achieved true, total closure. The remaining fifth or so of the crew's food, particularly meat, was brought in from outside because the system could not produce it. Human waste was, for the most part, not recycled back into the loop at all. It was dried and stored rather than broken down and returned to the soil to feed the next harvest, which means the loop was actually cut at one of its most important points. The cycle that a real generation ship would absolutely depend on, the full return of every nutrient from waste back into food, was simply left open, with the difficult end of it set aside. Biosphere was the closest we have ever come, and it was still a loop with the hardest part deliberately unclosed. And then there is the matter of time. The most important number attached to Biosphere is the length of its longest continuous run. With a crew of 3 sealed inside, living off the system, the longest closure lasted 180 days, 6 months. That is the record. That is, by one fair measure, the longest that human beings have ever lived inside a working, regenerating, closed loop of life, and it was achieved by importing meat and setting the waste problem aside in a chamber the size of a house, beneath a city, with the full resources of a research institute standing by to intervene the moment anything went wrong. Now place that record next to the requirement. A generation ship to the nearest star needs its closed loop to hold not for 180 days, but for something like 180 years, and then another 180, and then another, on and on for 10 or 20 or 40 generations. The gap between what we have actually demonstrated and what the dream requires is not a matter of doing a little better. It is a gap of 1,000-fold or more in time, and it is a gap that includes closing the very loops that every real experiment has left open. When you set the 6 months of our greatest success beside the centuries the journey demands, the distance between them is almost as hard to take in as the distance to the stars themselves. There is a deeper reason that stretching the time is so much harder than it looks, and it has a name that has come up in modern discussions of exactly this problem. It is sometimes called the metabolic rift, the slow drift of a sealed ecosystem out of the delicate ratios that life depends on. In a closed loop, the various elements that living things need, the carbon and nitrogen and phosphorus and the trace metals that appear in tiny but essential amounts all have to keep moving in balance. But real biological systems are messy, and over time these elements tend to wander. Some get locked up in forms that organisms cannot use. Some accumulate where they are not wanted and become toxic. The communities of microbes that drive the whole recycling process do not stay fixed either, because microbes reproduce and mutate and evolve at tremendous speed, and a microbial community sealed in a box for decades will not be the same community you started with. There is good reason to think this drift does not stay gentle, that it can accelerate, so that a closed biosphere might have a kind of natural lifespan, a stretch of time after which it tends to fall out of balance, no matter how carefully it was built. The contrast between the two great experiments is itself instructive. Biosphere 2 tried to recreate whole wild ecosystems, rainforests and reefs and savannas, betting that a miniature copy of Earth's natural variety would balance itself the way the real planet does. Bios 3 did almost the opposite. It was austere and engineered, built around a few carefully chosen, hard-working organisms, mainly the algae and the wheat, with the system tuned and monitored like a machine rather than left to find its own equilibrium. The Siberian approach, the simpler and more controlled one, is the one that achieved the longer and more stable closure of breathable air. That hints at something counterintuitive about how a starship's life support might actually have to work, that the path to lasting may run not through recreating the abundant complexity of Earth, but through ruthless simplicity, a stripped-down loop with as few moving parts as possible, because every part you add is another place for the drift to begin. Even so, the microbes would still be the wild card over centuries, and this is where even Bios 3's success runs into the wall of time. The algae and bacteria that do the real work of recycling reproduce in hours, not years, which means that over a long voyage, they would pass through an astronomical number of generations, far more than the humans aboard, and with each generation comes the chance of mutation and evolutionary change. The microbial community that keeps the air clean in the first century would not be the same community a few hundred years later, because it would have evolved drifting toward whatever served the microbes rather than whatever served the people. You cannot freeze evolution. You cannot ask a living system to stop changing. And a recycling loop built on organisms that are quietly evolving the whole time is a loop whose behavior in the distant future no one can fully predict or guarantee. If that is true, and the evidence we have leans uncomfortably in that direction, then it points to something genuinely disturbing about the whole generation ship idea. It suggests that the sealed biosphere might have its own clock, an expiration built into the chemistry, and that this clock could be far shorter than the voyage. You could build the perfect ship with the perfect engine and the perfect hull, and the living loop inside it could still quietly drift toward collapse somewhere in the 2nd or 3rd century, long before the destination came into view, not because anyone made a mistake, but because that may simply be how long a sealed loop can hold. We do not know whether that is the case. We have never run a closed system long enough to find out. The longest we have ever managed is 6 months, and even that one had its hardest loop left open. But the air is not the only thing aboard that has to keep cycling for centuries. There is another closed system on the ship, one made not of gases and nutrients but of people, and it turns out to be every bit as fragile. Part 6. The gene pool is a closed system too. Suppose, for the sake of argument, that we solve the air. Suppose we crack the chemistry of closure, build a biosphere that holds its balance for 1,000 years, grows abundant food, recycles every atom, and never lets the oxygen slip. Even then, a generation ship faces a second problem that is completely independent of the first, and it is one that no amount of engineering can simply build its way past. The problem is the people. Specifically, it is the problem of keeping a small, isolated population of human beings genetically healthy across all those generations when no new people can ever join them from outside. Because the crew, considered as a breeding population, is itself a closed loop, and closed loops of genes have their own ways of failing. To see why this is hard, you have to understand a little about what keeps a population genetically healthy in the first place. Every human being carries 2 copies of most of their genes, one from each parent, and scattered through everyone's genetic code are variants that are harmful when you happen to inherit 2 damaged copies of the same one. In a large population, this is rarely a problem, because the odds of 2 people who both carry the same rare harmful variant having children together are low, and there is so much genetic variety spread across millions of people that the bad combinations stay uncommon. Genetic health, in a sense, is a numbers game, and a large, well-mixed population wins it almost automatically. A small, sealed population does not have those numbers, and it faces 3 linked dangers that all grow worse over time. The first is called the founder effect. When you start a population with only a small group of people, that group carries only a fraction of the genetic variety of the species as a whole. Whatever variants those particular founders happen to carry, including any rare harmful ones, become the entire genetic inheritance of everyone who comes after. If 2 of your 100 founders happen to carry the same uncommon disease variant, that variant is now far more common on your ship than it ever was on Earth, baked into the population from the very first day, simply by the luck of who came aboard. The second danger is genetic drift. In a small population, the mix of gene variants does not stay stable from one generation to the next, because chance plays an outsized role in who has children and which genes get passed on. A useful variant can simply vanish by bad luck if the few people who carried it happen not to reproduce, or happen to have only sons, or are lost in an accident. In a population of millions, these random fluctuations average out to nothing. In a population of a few dozen or a few hundred, they can swing wildly, and over many generations they steadily erode the variety the population started with, narrowing the gene pool generation by generation, never to be replenished. The third danger is the one most people have heard of: inbreeding depression. As the generations pass on a sealed ship, everyone aboard becomes more and more closely related, because they are all drawing from the same small set of founders. Eventually, there are no distant strangers to marry, only cousins of varying degrees. And as relatedness climbs, so do the odds that 2 parents both carry the same harmful recessive variant inherited from a common ancestor, which means more children born with serious genetic conditions, lower fertility, and lower survival. Left unchecked across many generations in a small enough group, this can drag a population into a downward spiral where each generation is a little less healthy and a little less fertile than the one before, until the line cannot sustain itself at all. These are not speculative worries invented for science fiction. They are the bread and butter of conservation biology, the science of saving endangered species, which has spent decades grappling with exactly the question of how small a population can get before it is doomed. Out of that work came a famous rule of thumb, first proposed around 1980, often called the 5500 rule. The idea was that you need roughly 50 breeding individuals at an absolute minimum to avoid the immediate dangers of inbreeding depression in the short term, and roughly 500 to retain enough genetic variety for the population to stay adaptable over the long term, to keep enough raw material for evolution to work with. The exact numbers have been argued over ever since, with some researchers insisting the real figures should be more like 100 and 1,000, but the shape of the answer has held up. You need more people than your intuition suggests, and you need them managed with great care, or the closed loop of genes will slowly poison itself. So now the generation ship has 2 independent clocks running against it, and they have nothing to do with each other. There is the chemical clock the slow drift of the sealed biosphere toward imbalance, the threat that the air and the nutrients will fall out of step somewhere in the centuries ahead. And there is this second clock, the genetic one, the steady narrowing and degrading of a small population cut off from all new blood. A ship could keep its air perfect, and its crops abundant for 1,000 years, and still arrive carrying a population so inbred and so genetically frayed that it can no longer reproduce reliably, a healthy world delivering a dying people. Survival, it turns out, is not just a matter of whether you can breathe and eat. It is also a matter of the slow statistics of who is left to have children, and whether their children can have children, century after century, in a gene pool that can never be refreshed. It helps to make the genetic danger concrete with a single thread of reasoning. Imagine that, among your founding crew, just 2 people happen to carry one hidden copy, each of the same rare and serious recessive condition. On Earth, in a population of millions, those 2 would almost certainly never have met, let alone had children together, and the condition would have stayed vanishingly rare. But on a ship of 100 people, sealed for centuries, their descendants will inevitably intermarry, because eventually everyone aboard is descended from those same few founders. Generation by generation, that single hidden variant spreads through the family tree until a large fraction of the population carries it, and then children begin to be born with 2 copies, and the condition that was once one in many thousands becomes a common affliction of the ship. Multiply that by all the hidden variants that any group of founders unknowingly carries, and you see how a healthy starting crew can breed its way into a sickly people without anyone making a single wrong choice. This is why any honest plan for a generation ship has to confront something deeply uncomfortable, which is the deliberate management of human reproduction. To hold off genetic decline, you cannot simply let people pair off and have children as they please, as we do on Earth. You would need to actively manage who has children with whom and how many, steering the gene pool generation after generation to keep relatedness low and variation high, perhaps supplemented by banks of frozen eggs and sperm carried from Earth to inject fresh variation. The biology might be manageable, but the human reality of it, a society in which the most intimate decisions of family and love are subordinated for 1,000 years to the genetic accounting of the mission, is its own kind of heavy burden, a closed loop of control as confining in its way as the hull itself, which raises the obvious and urgent question. If you are actually going to do this, if you are going to seal a group of human beings into a ship and ask them to keep the species going for 1,000 years, with no one ever joining from outside, how many would you need to send? What is the minimum number of people that gives the gene pool a fighting chance to survive the voyage intact? It sounds like the kind of question that ought to have a clean answer, a single number that careful science could pin down. People have tried very hard to find that number, and the strange, almost unsettling thing is that their answers do not agree with each other, not by a little, but by a factor of several hundred. Part 7. The number nobody can agree on. For a long time, the question of how many people you would need to crew a generation ship was answered mostly by guesswork and gut feeling. Then, fairly recently, 2 scientists decided to attack the problem with actual mathematics. Frederick Marin, an astrophysicist in Strasbourg, and Camille Beloufi, a particle physicist, built a computer program they named Heritage. It was the first tool of its kind, a simulation designed to follow the genetic fate of a crew aboard an interstellar ship across the entire length of a voyage, generation by generation, accounting for births and deaths, for who pairs with whom, for the slow accumulation of inbreeding, for accidents and disease, all of it. And instead of running this simulation once, they ran it thousands upon thousands of times, each run a complete and slightly different history of a ship crossing the dark, so they could see not just what might happen but how often each outcome occurred. What Heritage let them do was ask a precise question. For a voyage of a given length, how large does the starting crew have to be so that the population reliably survives to the end, healthy and able to reproduce, without any outside genetic material ever being added? They modelled a long journey on the order of 6,300 years, and they ran the numbers under deliberately careful, conservative rules about how the crew would pair and reproduce. And the answer they arrived at, the headline number from their work, was startlingly small. Under their conservative model, a starting crew of about 98 people, that is 49 breeding pairs, was enough to give the voyage a near certain chance of arriving with a genetically healthy population. Below that number, the simulations began to show ships that failed, populations that drifted into terminal decline, and, in some runs, simply went extinct in the dark. But at 98, with careful management, the ship reliably made it. 98 people. If that figure surprises you with how small it is, you are not alone, and you should hold on to that surprise, because it is only half the story. Because another researcher, the anthropologist Cameron Smith, looked at the same problem for a project studying world ship design and came to a radically different conclusion. Smith's objection was not about the genetics in calm conditions, it was about disaster. A number like 98, he argued, might survive a smooth, undisturbed voyage where everything goes according to plan. But a real journey of centuries will not be smooth. Somewhere along the way, there will be an epidemic that sweeps through the close quarters of the ship. There will be an accident, a fire, a hull breach, a failure that kills a chunk of the population at once. There will be a bad stretch of harvests. And a crew of 98 has almost no margin to absorb a blow like that. Lose a third of them to a plague in the wrong generation, and the survivors may be too few, too related, to recover. So Smith ran the numbers, with catastrophe built in, asking not what is the minimum to survive a perfect voyage, but what is the minimum to survive a realistic one, with disasters factored as near certainties over a 1,000-year span. And his answer was not 98. It was something on the order of 14,000 to 44,000 people, with a comfortable target around 40,000. Tens of thousands, not dozens. A small city, not a large village. The two estimates, both produced by serious researchers working carefully on the same question, differ from each other by a factor of several hundred. I want you to sit with how strange that is. This is not a case where we are missing one decimal place, or arguing about whether the answer is 20 or 30. This is a disagreement between under 100 and over 40,000, between a number you could fit in a large house and a number that needs a city. And both numbers come from real analysis. The gap is not a failure of arithmetic. It comes from a genuine, unresolved question about what you are really planning for. If you assume the voyage goes well, you need shockingly few. If you assume the voyage will be struck by the kind of catastrophe that 1,000 years makes almost inevitable, you need a multitude. The honest reading of that enormous spread is not that one side is right and the other wrong. The honest reading is that nobody actually knows how many human beings it takes to keep our species alive in a sealed box for 1,000 years, because we have never done it, and the answer depends entirely on assumptions we cannot test. Let me try to make the stakes of that uncertainty something you can feel rather than just something you know. Imagine that you could watch every possible version of the voyage at the same time. The simulation begins, and 10,000 ships ignite at once, each one appearing as a thin thread of light, and each thread is a complete history of a sealed world crossing thousands of years of dark toward the same distant star. Now speed it up, so that generations flicker past as a pulse. Watch the threads. Many of them hold steady, their populations rising and falling gently around a stable number, breathing in and out, century after century, the light along them never wavering. but watch closely and you will see others begin to dim. Here is a thread where the founders happen to carry too many of the same hidden flaws, and inbreeding set in early. There is a thread where genetic drift, by sheer bad luck, narrowed the gene pool one generation too far. Over here is one where a single epidemic, arriving at the wrong moment, took exactly the wrong people. One by one, those threads flicker and go dark, each extinguished line a ship that set out full of music and plans and children and arrived as a silent tomb, or never arrived at all. When the run finally ends, and you count how many threads are still burning, you have your answer, and it is not a single number, but a fraction, a probability. The crews that started too small went dark far more often than not. What you are looking at, in that field of dying lights, is the survival of a species rendered as a statistic. That is the moment the dream changes character, and I think it is worth being honest about why it lands so hard. As long as the generation ship is an adventure, a brave voyage to a new world, everyone aboard is a hero in a story. But the simulation strips that away and shows you what they actually are in the cold logic of the thing. They are data points in a survival curve. The people aboard, the ones who will be born and fall in love and raise children and grow old in those corridors, are entries in a probability table, and some fraction of those tables end in extinction no matter how brave anyone is. The question is no longer whether they will have a wonderful journey. The question is whether their particular thread is one of the ones that stays lit, and that is a question that careful, decent, brilliant scientists cannot answer within 2 orders of magnitude. We do not know if you need 100 people or 40,000. We only know that the people we sent would be living their whole lives inside the margin of our uncertainty. It is worth understanding what heritage quietly assumes in order to reach a number as small as 98, because the assumptions are nearly as revealing as the result. The simulation does not model a crew living and loving freely. It models a crew under careful reproductive management, where pairings between close relatives are forbidden, where the timing and number of children are regulated to keep the population stable and the gene pool as varied as possible. In other words, the small number only works if the people aboard surrender a great deal of their reproductive freedom to the needs of the mission, for every generation without exception. The 98 is not a number of free people. It is a number of carefully managed ones. The reason Cameron Smith's estimate balloons into the tens of thousands is that he refuses to assume the voyage goes smoothly, and 1,000 years is more than long enough to make that refusal wise. Over 10 centuries, the odds that the ship escapes every epidemic, every fire, every reactor scare, every stretch of failed harvests, every violent upheaval among the crew, are essentially 0. Something will go wrong, probably many things, and when a disaster strikes a population of 98, it can erase the margin entirely, leaving too few survivors, too closely related, to recover. A population of tens of thousands can lose thousands and carry on. The enormous gap between the 2 estimates is really a gap between 2 different bets about how kind the universe will be to a small sealed world over 1,000 years, and the whole weight of everything we have seen tonight suggests the universe is not kind to sealed worlds at all. And even if we guessed the number right, even if the air held and the gene pool stayed healthy, there would still be the ship itself to contend with. Because 1,000 years is a very long time, not just for a biosphere and not just for a bloodline, but for metal and machinery and every physical thing the people aboard depend on to stay alive. Part 8. The ship ages like a body. We have been talking about the living systems aboard the ship, the air and the crops and the people, but underneath all of them is the ship itself, the hull and the structure and the machines, and metal has its own way of dying. We tend to think of a spacecraft as a fixed, permanent thing, a solid object that simply persists. But nothing persists for 1,000 years without maintenance, and out in interstellar space, the forces working to wear the ship down never rest, even while the people inside are sleeping. Begin with radiation, because it is relentless and it is everywhere out there. Here on Earth, we are protected by two great shields, the planet's magnetic field and the thick blanket of the atmosphere, which together deflect and absorb most of the dangerous particles streaming through space. A generation ship has neither. Once it leaves the protection of the Sun's inner region, it is exposed to the full force of galactic cosmic rays, the atomic nuclei flung across the galaxy by exploding stars and other violent events. Traveling at nearly the speed of light, plus the bursts of energetic particles thrown out by stars themselves. Measurements taken by spacecraft traveling between the planets give us a sense of the dose, and it is sobering. Unshielded, the radiation exposure in space runs on the order of half a sievert per year, a level that, sustained over a human lifetime and across generations, would be both lethal and mutagenic, damaging the very genetic code we just spent so long worrying about preserving. What makes cosmic radiation especially cruel is that it is hard to block, harder than you might expect, and in a way that is almost perverse. If you put a thin shield in the way, a layer of metal, say, a fast, heavy cosmic ray nucleus does not simply stop. It smashes into the atoms of the shield and shatters them, producing a spray of secondary particles, a shower of fragments that can be more numerous and in some ways more harmful than the single particle you were trying to stop. So a little shielding can actually make things worse. To truly protect the crew, you need a great deal of mass between them and space, meters of water, or rock, or packed regolith, wrapped around the living quarters like the walls of a bunker. And mass, on a ship, is the most precious and expensive thing there is, because every kilogram has to be accelerated and carried for the entire voyage. The protection the crew needs is measured not in centimeters of clever material, but in meters of sheer bulk. Then there is the slow wearing down of the ship's own body. Over centuries, a spacecraft is sandblasted by the thin scatter of dust and micrometeoroids it sweeps up as it moves, each tiny impact carrying enormous energy at interstellar speeds, slowly eroding any exposed surface. The constant bombardment by radiation does not only threaten the crew, it embrittles materials, changing the structure of metals and plastics at the atomic level, making them more likely to crack. Metal flexed and stressed, over and over, by the spin that provides artificial gravity, by temperature changes, by the simple operation of the machinery, suffers fatigue, the same process that eventually cracks a paperclip you bend back and forth. Seals creep and lose their grip. Bearings wear down. Electronics degrade as the radiation flips, bits, and damages circuits. None of this is dramatic on any given day. All of it is certain over centuries. And here is the part that makes it so much harder than aging on Earth. On Earth, when something wears out, you replace it. You order a part, you call a repair crew, you send the broken machine to a shop. The generation ship has none of that. There is no dry dock waiting at the halfway point. There is no factory that can ship a replacement reactor component. Whatever breaks must be repaired with what is already aboard, and whatever is used up to make a repair must itself be replaced from the ship's own recycled materials. This means the ship cannot just carry spare parts, because no finite store of spares could cover 1,000 years of failures. It must carry the ability to make spare parts, to mine and refine and shape new components out of its own substance, recycling the old into the new, indefinitely. The ship needs to be, in effect, its own factory, and its own repair crew, and its own mine, a closed industrial loop layered on top of the closed loop of life. And that industrial loop is subject to exactly the same relentless pressure of wear and entropy as everything else. This is why the serious engineering studies of world ships, when they actually run the numbers, arrive at conclusions that sound less like spaceflight and more like the founding of a civilization. The vessels they describe are not sleek craft but enormous structures, massing tens of millions of tons, the great majority of that mass being shielding and structure and the closed ecosystem rather than anything to do with propulsion. They conclude that such a ship is only feasible if it possesses sophisticated automatic repair and manufacturing systems capable of rebuilding the ship's own components on the fly. And they reach a blunt overall verdict, which is that a true world ship is not something our civilization could build. It is a project for a culture far wealthier, far more technologically mature, and far more patient than ours, a culture that has mastered closed systems on every level at once. Consider one specific source of wear that most people never think about, the spin that gives the ship its gravity. A generation ship almost certainly cannot coast in weightlessness for centuries, because the human body decays without gravity, bones thinning and muscles wasting, so the ship would likely rotate to press its inhabitants outward against the hull and mimic the pull of the ground. But rotation means the entire structure is under constant mechanical stress, year after year, century after century, and every joint and seam and bearing involved in that spin is being worked the way you work a wire by bending it. Metal, under repeated stress, develops fatigue, microscopic cracks that grow with each cycle until, without intervention, something finally gives. The very system that keeps the crew healthy is also a relentless source of structural aging, grinding away at the ship for the entire length of the voyage. There is also a brutal arithmetic of reliability hiding in the numbers. A ship like this would contain many thousands of critical components, each with some small chance of failing in any given year. On Earth, that is fine, because each failure is repaired or replaced and life goes on. But string thousands of components across 1,000 years, and the number of failures the ship must successfully absorb climbs into the millions. Every one of those millions of repairs must succeed, using only materials and skills available aboard, with no outside help, because a single unrepaired failure in the wrong system, the reactor, the air, the hull, can end everyone. This is why the engineering studies insist that such a ship must essentially repair itself automatically and continuously forever. The ship cannot be a thing that is maintained. It has to be a thing that maintains itself, a closed industrial loop as flawless and tireless as the closed loop of life. And we have never built a machine that can keep itself running untended for even a single century, let alone 10. So we add a third clock to the two we already had. There was the chemical clock, the drift of the biosphere. There was the genetic clock, the narrowing of the bloodline. And now there is the mechanical clock, the steady aging of the hull and the machinery, the certainty that over 1,000 years, even the metal grows old and brittle and tired, with no shipyard anywhere to set it right. Notice that all three clocks point the same direction, the direction the second law always points, toward disorder, toward breakdown, toward the slow unwinding of anything that is sealed and left to run. The enemy was never the distance. The enemy is the patient erosion of everything, working from the inside, working on the air and the genes and the steel alike. And yet, as heavy as all of this is, the most haunting failure of a generation ship may not be any of these physical ones. It may be something stranger, something that can rot away even while the air stays sweet and the hull stays sound and the people stay healthy. It is the possibility that the ship could forget where it is going. Part 9. The Ship That Forgets. So far, every threat we have considered has been physical. The air thinning, the gene pool narrowing, the metal growing brittle. These are failures you could measure with an instrument, point to on a gauge, but a generation ship carries something else that has to survive the centuries, something that cannot be stored in a tank or shielded behind a wall of water, and it may be the most fragile cargo of all. The ship has to carry knowledge. It has to carry the understanding of how every one of its systems works, the skills to repair them, the science behind them, and underneath all of that, it has to carry the memory of why the voyage is happening at all. And knowledge, it turns out, is just as much a closed loop as the air, and just as prone to drift and decay. Think about what is required to keep a complex technical society running across 30 generations with no help from outside. The first generation, the ones who designed and built and boarded the ship, will understand it completely. They will know why the reactor is built the way it is, how the recycling plant manages its chemistry, what to do when a particular warning light comes on, and why. But they cannot pass that understanding directly to the people who will be aboard in the year 3000. They can only teach their children, who will teach their children, who will teach theirs, in an unbroken chain of instruction that has to hold for 1,000 years, with no textbook ever arriving from an outside university, no expert ever flown in to consult, no way to check the ship's knowledge against any source beyond itself. Every link in that teaching chain is a chance for something to be simplified, misunderstood, forgotten, or quietly lost. We know how this goes because we have watched it happen on Earth, in slower motion, all through history. Languages drift. The way people speak changes generation by generation, until the speech of ancestors only a few centuries back becomes difficult and then impossible for their descendants to understand without special study. Skills vanish when the last person who held them dies without passing them on. And humanity has lost technologies and crafts and techniques this way many times over, knowledge that had to be painstakingly rediscovered or that is simply gone. Now, imagine that process running inside a sealed ship where the population is small, where there is no larger civilization to preserve a backup, where a single bad generation, a war, a plague, a period of upheaval that interrupts the schooling of the young, could break the chain of technical knowledge permanently. And once it is broken, there is no one outside to restore it. This is the real seed of truth, inside a scenario that has haunted science fiction for as long as the idea of the generation ship has existed. It is the story of the ship whose crew forgets that they are on a ship at all. Generations into the voyage, the people aboard no longer understand what their world is. They have lived their whole lives inside the hull, as did their parents and their grandparents back further than anyone remembers, and the truth of the mission has decayed from knowledge into legend, into myth, and finally into nothing. They believe the ship is the entire universe. They think the metal sky is the only sky there has ever been. The controls, if anyone can still operate them, are tended as religious rituals whose original purpose is lost. It is fiction, but it dramatizes something real and frightening, which is that the purpose of the voyage is not a physical object that endures on its own. It is an idea held in living minds, and it has to be deliberately maintained, taught, and believed every single generation, or it evaporates. Let me take you to a moment that captures what this kind of failure would actually feel like, not as a disaster, but as something quieter and sadder. Stand for a moment beside a child born in the 4th century of the voyage. To you, the word outside means something immediate and physical. It means a sky overhead, a horizon in the distance, that line where the land meets the air. But to this child, the word means nothing at all. It is a word from an old story, like the words ocean or rain or mountain, sounds that refer to things she has never seen and cannot really picture. She has never in her life stood anywhere that was not a corridor or a chamber. The viewport beside her shows only black, scattered with unmoving points of light that have never once grown closer in her entire life and never will in her lifetime. Her world is the hull, and the hull is everything. It is the floor and the ceiling and the weather and the law. She knows the great recycling plant at the ship's center the way you know the sky, simply as the way things are, not as a machine that someone designed for a reason. And if you asked her where the ship is going, she might tell you a story, half believing it, the way we all half believe the oldest stories we were told as children. Meanwhile, the machinery still hums, the air still holds, the crops still grow. By every physical measure, the ship is succeeding. And yet something essential has already failed, generations before anyone could possibly arrive, because the thing the whole voyage was for has thinned away into a legend that no one quite believes. That is a different kind of loss than running out of air, and in some ways it is more unsettling, because it reveals a gap we do not usually notice between two things we tend to lump together. There is the survival of the ship, and there is the survival of the mission, and they are not the same thing. A ship can hum along in perfect physical health. Lights on, air sweet, harvests coming in, population stable, every gauge reading green, while the reason it exists quietly drains out of the minds of the people aboard. The cruelest failure of a generation ship might not be a hull breach or a famine or a plague at all. It might be a generation, somewhere in the long middle of the voyage, that no longer remembers it is going anywhere, that has come to mistake the corridor for the cosmos, that lives and dies, tending a vessel whose destination has become a forgotten word. The mission would be dead, in every way that matters, while every person aboard was still alive. The speed at which language alone can drift is enough to make the point. The English of just 5 or 6 centuries ago is already a strain for a modern reader, full of words that have shifted meaning or vanished, spellings and grammar that feel foreign. Go back 1,000 years, and the ancestor of English becomes effectively a different language, unreadable without special training. Now picture that same process running inside a small, isolated population with no outside contact to anchor it, where the speech could drift even faster. The crew of the late voyage might struggle to read the words their founders wrote, the operating manuals, the warnings, the very instructions for keeping the ship alive, growing more obscure with every passing century, like sacred texts in a forgotten tongue. What tends to survive longest, ironically, is the how without the why. People can be taught to perform a procedure, to flip the right switches in the right order, long after anyone remembers what the procedure is for or how it works underneath. Ritual outlasts understanding. And that is a dangerous condition for a ship to be in, because the moment something fails in a way the manuals did not anticipate, you need people who grasp the underlying principles, who can reason their way to a fix, not people who only know the memorized steps. A crew that has kept the rituals but lost the understanding can run a ship beautifully right up until the first surprise, and then discover they have no idea how to save themselves. Add to this the problem of governance, the challenge of keeping a just and stable society across 30 generations in a closed world, with nowhere for dissenters to go, and you see that the social machinery is every bit as prone to breakdown as the mechanical kind, and far less amenable to repair. What that forces you to confront is that purpose is perishable. We assume that meaning, once established, simply persists, that if you launch a ship toward a star, the going toward a star is a permanent fact about it. But meaning lives only in minds, and minds are replaced every generation, and anything that must be handed from mind to mind across 1,000 years can be dropped. Purpose, it turns out, is as much a consumable as oxygen. It has to be regenerated continuously, taught and retaught, or it runs out. And there is no instrument on any control panel that measures how much of it is left. So even a ship that solves the air, the genes, and the metal could still fail at the one thing none of those solve, which is remembering why it left. But suppose, against all of this, that a ship somehow held everything together, the air, the bloodline, the steel, and the memory, all the way across the centuries. There is still one more cruelty waiting, and it is perhaps the strangest of them all, because it is a way the voyage could be rendered pointless, even if absolutely nothing aboard ever went wrong. Part 10. The Ark that is already obsolete. Imagine that we have done everything right. We have built a world ship that holds its air for 1,000 years, keeps its gene pool healthy, repairs its own aging body, and faithfully passes down the knowledge and the purpose of the mission, generation after generation, without a single break. Imagine the impossible has been achieved, and the ship is a perfect, self-sustaining success, sailing serenely toward its distant star, with everything aboard functioning exactly as intended. Even then, there is a trap waiting, and it has nothing to do with any failure on the ship. It is a trap that comes from the world the ship left behind, and from the simple fact that the world keeps improving after you are gone. The problem was laid out carefully in 2006 by a thinker named Andrew Kennedy in a piece of reasoning he called the weight calculation. It begins with an observation about how technology tends to develop, which is that the speeds we can achieve generally improve over time, often in a way that compounds, growing by some percentage each year, rather than by a fixed amount. If that pattern holds for spacecraft, it leads to a deeply unsettling conclusion. Suppose you launch your generation ship today, at the best speed today's technology allows, on a voyage that will take 1,000 years. Back home, your civilization keeps developing. A century after you leave, they have ships that are substantially faster. 2 centuries after you leave, faster still. And at some point, a ship launched long after yours, traveling much faster than yours ever could, will overtake you in the dark, sail right past your slow arc, and arrive at the destination first, perhaps centuries before you, while your descendants are still mid-voyage. Follow that to its end, and you find something genuinely strange. The first generation ship might arrive at its new world only to discover that the world is already settled, that it was colonized generations ago by people who left Earth long after the Ark did, but in faster ships. Everyone aboard the original vessel would have given up their entire lives and the lives of all their children across the centuries for a voyage that turned out to be unnecessary, beaten to the goal by travelers who had the patience to wait for a better ride. The dream of being the brave first pioneers would curdle into the reality of being the slowest boat that everyone else passed on the way. Kennedy worked this out quantitatively, using a journey to Barnard's star, about 6 light-years away, as his example. And he found something that has the shape of a genuine paradox. Because waiting for faster technology can let you arrive sooner, but waiting too long means you have simply delayed without benefit, there is an optimal time to depart, a mathematically best moment to leave, so as to arrive at the earliest possible date. For his example journey, factoring in the expected growth of travel speed, he calculated that the minimum total time to reach Barnard's star, counting both the waiting and the travelling, came out to roughly 712 years from the time he was writing. The counterintuitive lesson is that a voyage begun immediately is very often the wrong move, because it commits you to today's slow speeds for the whole crossing, when a later launch on a faster ship would lap you and reach the destination first. This creates what you might call an incentive never to leave, or at least never to leave yet. Every generation that contemplates launching an ark faces the same reasoning. If we go now, we lock ourselves into current speeds, and our grandchildren, with their better ships, will overtake us and arrive before our own descendants do, making our sacrifice pointless. So perhaps we should wait until the technology is better. But that same logic will apply to the next generation and the one after that, each of them with the same good reason to wait a little longer for a faster ship. The result is a kind of trap, where the rational choice in any given century is always to wait, and the great voyage keeps being deferred to a future that, by its own logic, also has reason to defer it. The ship that would actually be worth launching is always the one you build later, which means the ship is always launched later, which means perhaps it is never launched at all. There is something almost cruelly elegant about this, because it is a way for the generation ship to fail that requires nothing aboard to go wrong. The air can be perfect, the people healthy and happy, the mission remembered and cherished, the hull sound, and still the entire enterprise can be rendered meaningless by the simple, continued progress of the civilization back home. It is failure by being overtaken, failure by obsolescence, the voyage made pointless not by entropy or accident, but by the very forward march of the technology that made the voyage thinkable in the first place. The faster your civilization advances, the more certain it becomes that any ship you launch will be passed by a better one. Progress itself becomes the thing that defeats the pioneer. There is a quiet, almost philosophical sting in the weight calculation that goes beyond the engineering. It suggests that the very impulse that would drive a civilization to attempt the stars, its restless drive to improve and accelerate, is the same impulse that keeps undermining the attempt. A culture advancing fast enough to dream of starships is, almost by definition, advancing fast enough to render each starship obsolete before it arrives. The faster you run toward the goal, the more certain it becomes that a future version of you will overtake the version that set out today. Progress does not just fail to help the first pioneers. Progress is precisely what dooms them to be passed. Imagine the psychology of it for the people aboard, which is its own slow cruelty. A family living in the 3rd century of the voyage, doing everything right, keeping the ship alive, raising their children to the mission, might look out through a viewport one day and see a light that is moving, a faster ship, launched generations after theirs, sliding past them in the dark on its way to the world they have given everything to reach. They would arrive to find the welcome already worn smooth by people who left home long after their own ancestors did. Everything their line had sacrificed, every life lived and ended inside that hull, would have brought them nothing but the knowledge that they were the ones who left too soon. It is a way for the voyage to break the spirit of its crew without a single system ever failing. There is even a way this idea brushes up against one of the oldest puzzles in all of astronomy, the strange silence of a galaxy that ought, by some reckonings, to be full of voices. If every advanced civilization that contemplates crossing the stars runs into the same weight calculation, the same endless rational reason to delay launching until the technology is just a little better, then perhaps that is part of why no one seems to have come. Not because they cannot build the ships, but because the cold logic of progress always whispers that next century's ship will be the one worth boarding, and so the great voyages keep being postponed by everyone, everywhere, forever. I want to be careful here, because this is speculation layered on speculation, and the silence of the sky has many possible explanations. But it is at least a haunting thought that the same restless cleverness that lets a species dream of the stars might be the very thing that keeps it forever on the launch pad, always about to leave, never quite leaving. And notice how this connects back to everything we have been circling all night. We keep finding that the obstacles to the generation ship are not really out there in the gulf between the stars. The distance just sits there, indifferent. The real difficulties are all relational and internal. The drift of sealed systems, the narrowing of an isolated bloodline, the aging of the unmaintainable machine, the fading of remembered purpose, and now this, the way a slow ship is undone by a fast world it can no longer see. The enemy was never the distance. The enemy is time, and what time does to anything that has to last, whether that thing is a tank of air, a family line, a steel hull, a shared memory, or a head start that a faster vessel will inevitably erase. Which leaves us with a hard question to face directly. After all of this, after every clock we have set ticking against the arc, we have to ask whether the whole idea is simply impossible, and if it is not impossible, what it would actually take to make a world that lasts. The answers, it turns out, take us in two very different directions, and the second one leads somewhere I do not think you will expect. Part 11. The Verdict and the Escape Hatches. There is a serious case to be made that the generation ship simply cannot work, and it deserves to be heard at full strength before we try to rescue the idea. The argument has been made most forcefully, not in a technical paper but in fiction, by writers who thought hard about closed worlds, and it has been repeated by ecologists who study how living systems actually behave. The case goes like this. A closed ecology does not just risk falling out of balance, it tends toward falling out of balance, inevitably, because no sealed system of that complexity can be perfectly regulated, and the small drifts compound until the whole web reorganizes itself into something the humans aboard did not design and cannot survive. An isolated human population does not just risk genetic decline, it tends toward decline, and toward what some have darkly called devolution, a narrowing and coarsening of the species in a small box. And layered on top of these biological arguments is a moral one that is harder to wave away than any equation. That moral problem is the question of consent. The people who choose to board a generation ship can consent to their own fate, however strange it is. But they are also deciding the fate of everyone who will be born during the voyage. Dozens of generations of human beings who never agreed to live their entire lives sealed in a metal world, never agreed to be born into a moving box with no sky, no choice of where to live, no option to leave, conscripted before birth into a mission they had no part in choosing. Every child born in transit is born into a sentence none of them was asked about. You can argue that all of us are born without consenting to the circumstances of our birth, that no child chooses its country or its century. But there is something different about deliberately engineering, in advance, 1,000-year span of human beings whose entire range of possible lives has been narrowed to the inside of a hull for the sake of a destination they will never see. It is one of the few places where the romance of the idea runs directly into a wall of genuine ethical unease. So that is the pessimist's verdict, and it is a respectable one. Closed ecologies degrade, isolated populations decline, and the unborn cannot agree to any of it. But notice that the strongest version of the claim says the generation ship can never work, and never is a very large word. Never is a claim about the absolute limits of engineering and biology, and it is a claim we have not actually tested, because we have never built a true closed world and run it for centuries. The honest position is not that we know it is impossible. The honest position is that everything we have tried suggests it is much harder than the dream admits, and that we have no proof it can be done at the scale and duration required. That is a different and more uncomfortable place to stand than either confident optimism or confident despair. Faced with how hard the multi-generational problem is, people who think seriously about reaching the stars have proposed a set of clever ways around it, and it is worth looking at them because each one teaches the same quiet lesson. The first is to skip the living crew entirely and send life in a dormant form. Instead of a population of people having children for 1,000 years, you carry frozen embryos, or the cells to make them, along with the machinery to gestate and raise the first human generation only when the ship nears its destination. This neatly sidesteps the genetic drift of a multi-generational crew, because there is no multi-generational crew. But it replaces that problem with one at least as daunting: the challenge of machines incubating, birthing, and raising healthy human children with no living parents, no human culture to grow up inside, no one to teach them what it means to be a person. You have traded a problem of biology for a problem of raising a generation of humans by machine, which no one has any idea how to solve. The second escape hatch is to put the crew to sleep. If you could slow human metabolism dramatically, place people into a true long-term hibernation or suspended animation, then a small crew, or even the whole complement, could sleep through the centuries and wake near the destination. No generations required, no aging, no drift. This shrinks the life support problem and erases the genetic one. But it depends on a technology that does not exist and may not be possible. The safe suspension of human biology for hundreds of years without the body decaying, a feat far beyond anything medicine can currently do for even a few hours, let alone centuries. The third hatch is more radical still. The idea of carrying the crew not as bodies at all, but as information, minds recorded as data, to be reinstantiated in new bodies or machines at the far end. This dispenses with biology entirely. It also assumes that a mind can be captured and copied and run as data, which remains pure speculation, untethered to anything we can actually do. The charge of devolution deserves to be taken seriously rather than dismissed, because it follows from real biology. In a small, sheltered, isolated population, the pressures that shaped human beings on Earth would relax and change. Traits that mattered on a planet might drift or fade in a hull where they no longer help survival, and new pressures, the particular demands of life in a sealed world, would begin to reshape the population in ways no one chose or could foresee. Over enough generations, the people who arrived might be measurably different from the people who left, not necessarily lesser, but altered, shaped by the box, no longer quite the species that boarded. Whether you call that devolution or simply evolution in a strange direction, it means the cargo that arrives is not guaranteed to be the cargo that was sent. And the reason scale is the only answer that seems to help is worth dwelling on, because it reframes what a starship even is. Every clock we have set ticking tonight, the air, the genes, the metal, the memory, runs slower and safer the larger the world is. A bigger biosphere drifts more gently and has more reserve. A bigger population resists genetic decline and absorbs catastrophe. A bigger society preserves knowledge through redundancy, many teachers instead of few. The only generation ship that the most careful thinkers consider survivable is one so enormous that it stops being a vehicle and becomes a small world, a hollowed asteroid, or a spun habitat holding a population the size of a city, with margin built into everything. But that is also an admission of defeat for the romantic version of the dream, because it means a true ark is not a ship a brave crew builds and boards in our lifetimes. It is a civilization-scale undertaking belonging to a future so much wealthier and more capable than us that we can barely imagine it if it belongs to anyone at all. And the fourth response is simply to make the ship so enormous that it stops being a ship and becomes a small world in its own right, a hollowed-out asteroid or a spinning habitat the size of a region, carrying not 100 people or a few thousand, but hundreds of thousands, with enough redundancy in its ecology, its gene pool, and its store of knowledge to absorb the failures that would doom anything smaller. This is the version that the most serious engineers consider the only potentially survivable one, precisely because scale buys margin against every clock we have discussed. And it is also the version most hopelessly beyond our reach, a project requiring resources and patience and mastery that lie centuries or more in our future, if they lie in our path at all. Look at the whole set of escape hatches together, and the pattern is unmistakable. Every single one of them works by converting the closure problem into a different unsolved problem. Frozen embryos trade it for machine parenthood. Hibernation trades it for indefinite human stasis. Mind uploading trades it for digital consciousness. The giant world ship trades it for a civilization-scale construction project we cannot begin to fund. The closure problem does not get solved by these ideas. It gets moved. And the fact that every exit leads back to another locked door tells you something about how fundamental the difficulty really is. Which brings us, finally, to the question underneath all the others, the one that has been waiting at the bottom of this the entire time. Part 12. The only ark that ever arrived. Step back now, all the way back, and look at the whole shape of what we have found. We set out to ask how long a generation ship could last, and what we discovered is that the question does not have one answer because the ship does not have one clock, it has many. There is the air, which Biosphere 2 showed us can begin to fail in months. There is the gene pool, whose minimum size we cannot pin down within a factor of several hundred. There is the metal of the hull, aging and embrittling with no shipyard to mend it. There is the chain of knowledge and the memory of purpose, which can fade from living minds even while every machine still runs. And there is the slow world left behind, capable of overtaking and obsoleting the whole voyage without anything aboard going wrong at all. The lifespan of a generation ship is not set by the strongest of these systems. It is set by whichever one fails first. The arc is only as durable as its weakest loop, and the unsettling truth is that we have never managed to keep any of those loops closed long enough to know which one would break or when. That is the answer to the title, As Honest as I Can Make It. We do not know how long a generation ship could last, and we cannot know from theory alone, because every part of the answer depends on keeping a complete, sealed, self-repairing world stable for a span of time that no human project has ever come close to sustaining. We are not waiting on a better engine. We are waiting on a kind of stability we have never once demonstrated in any system, at any scale, for anything like the required length of time. The generation ship is not really a propulsion problem in disguise. It is a problem about whether order can be held against the steady pressure of entropy inside a box that is cut off from everything else. And on that question, the evidence we have is not encouraging. But here is where the whole thing turns, and where I want to leave you tonight, because there is one more piece of evidence we have not yet considered, and it changes everything. We have been speaking as though no one has ever successfully built and operated a generation ship. That is not quite true. There is exactly one that has worked. You are riding on it right now. Consider, for a moment, what the planet beneath you actually is. It is a self-contained world, carrying living passengers through space. It moves, and not gently. It carries roughly 8 billion people, along with every other living thing, in an orbit around the center of the galaxy at something close to 500,000 miles an hour, a voyage with no destination anyone aboard will ever reach. It has kept its air breathable, its water cycling, its temperature livable, and its web of life in balance, not for the centuries a starship would need, but for billions of years through catastrophes that would have ended any fragile sealed habitat many times over. No one who was aboard at the beginning lived to see where it was going. No one alive now will either. Every generation is born on it, lives its whole life on it, and dies on it, handing the journey to children who do the same. By every definition we have used tonight, the Earth is a generation ship, and it is the only one that has ever demonstrably worked. So why does this one succeed where every ship we imagine seems destined to fail? The answer is the single thing that every sealed starship lacks, and once you see it, you cannot unsee it. The Earth works because it is not closed. 93 million miles away, a star pours an unimaginable torrent of energy onto this world every second of every day, and has done so without interruption for billions of years. That constant stream of sunlight is what drives every cycle that keeps us alive. It lifts the water into the sky to fall again as rain. It powers the plants that make our oxygen and our food. It runs the great loops of carbon and nitrogen and life. It is, quite literally, what pays the entropy bill, what allows this world to hold its astonishing order against the universal slide toward disorder, year after year, age after age. The Earth is not a sealed bottle keeping its contents alive by some internal magic. It is an open system drinking energy from a star, and that openness is the entire secret of why it lasts. Let me bring you to the realization the only way I know how, which is to ask you to step all the way outside the imagined ship one last time. Picture the great ark we have been worrying over all night, the sealed city in the dark, and now let it shrink, let it recede, until it is a speck, and then nothing, and turn your attention instead to the world under your own body as you lie there. You are already aboard a generation ship. It is enormous and ancient and improbably, gloriously functional, and it has solved the problem that defeats every vessel we try to build, the problem of lasting. And it solved that problem not by being more perfectly sealed, but by being open, by never being a closed bottle at all, by keeping a window flung wide to a star that pours order in faster than entropy can drain it out. The bottle was never sealed. That was always the trick. If you are somewhere you can feel it, notice the warmth of light on your skin, sunlight, or the memory of it, and understand at last what it is actually doing. It is not just light, it is the thing holding your entire world together, the open channel that lets a closed-seeming planet keep its passengers alive across a journey of billions of years. What the Earth does, that no sealed ship has ever managed, is regulate itself. Across billions of years, through asteroid impacts and ice ages and the slow brightening of the sun, the living world and the planet beneath it have together kept conditions within the narrow band that life can tolerate, the temperature livable, the air breathable, the chemistry in balance, not by any plan, but by an immense web of self-correcting cycles powered by that steady stream of starlight. It is the only example we have ever seen of a world-sized life support system that actually works over the timescales a starship would need, and it achieves that stability through staggering scale and constant external energy, the two things every artificial ark most conspicuously lacks. There is a humility in this that I find strangely comforting rather than bleak. We tend to imagine that lasting means sealing yourself off, fortifying, closing the doors against a hostile universe. The lesson of the generation ship is the opposite. The things that try hardest to be self-contained are the ones that fail soonest, and the one world we know that has truly endured is the one that never stopped drinking from something larger than itself. Our planet does not survive by holding the universe out. It survives by staying open to it, by letting a star reach across 93 million miles to pour in the order that keeps everything turning. The ark that arrives is not the one with the strongest walls. It is the one that was never really sealed at all. And so the question we began with quietly transforms in our hands, the way the best questions do. We started by asking how long a ship could last out there, sealed against the dark. We end somewhere else entirely, having learned that the ships which try to seal themselves against the universe are exactly the ones that cannot endure, and that the only world we know of that truly lasts is the one that stays open to it, fed and warmed and held together by a fire it does not contain. The enemy was never the distance. The enemy was always the sealing, the cutting off, the attempt to be a world unto oneself. We went out looking for how to build a vessel that could carry life across the centuries, and we found that we were already standing on the answer, that it has been carrying us the whole time, and that it is more fragile and more precious and more dependent on that distant star than we usually let ourselves feel. How long could a generation ship last out there? We still do not know, but we know the one that works, and we know why it works, and tonight, perhaps, you will fall asleep aboard it, a little more aware of the quiet, constant, open miracle that keeps it sailing on.